Hello guys, welcome back to another video. And today we're actually going to introduce and prove the very notorious or famous product called the Wallis product, which is another representation for pi, but in terms of products, because pi can be expressed as the Leibniz series, which is an infinite sum, and the Wallis product is different because it's an infinite product. So let's get started as always. Okay, so to start with, um, I won't state what the Wallis product is directly. I will actually give an example of why we need to care about it. What's the basic idea we need to first look at before coming across the Wallis product. So, say we have an integral I defined as integral from 0 to 1 of x minus 1 over natural log of x times x plus 1 dx. Okay, so you know if there was no natural log over here, we would just have a polynomial divided by a polynomial. In this case both are linear, so we'll have a linear divided by a linear, and it would be really convenient to solve that. So to get rid of the natural log, we can actually use the Feynman rule of Feynman technique of integration, or the Leibniz rule of differentiating under the integral sign. We can actually have a parameterization of an exponential function, and you'll see in a minute why. So x minus 1 times x to the t divided by natural log of x times x plus 1 dx. So when you take the partial derivative with respect to t of this, integral from 0 to 1 now becomes x minus 1 times x to the t times natural log of x by the chain rule. Differentiating x to the t will give you natural log of x times that same term divided by natural log of x times x plus 1 dx. And the the entire idea behind using this exponential as a parameterization was to cancel the natural log, and we actually did that. So we now have integral from 0 to 1 of uh, x minus 1 times x to the t divided by x plus 1 dx. So at this point, what I'm going to do is I'm going to distribute the x to the t with the term in the bracket. So we have integral from 0 to 1. We have x to the t plus 1 minus x to the t divided by x plus 1 dx. And noticing the limits, the bounds of integration are from 0 to 1, which means, and having a denominator as 1 plus something or 1 minus something, we can actually look at implementing the geometric series. So I'm just going to rewrite this as x to the t plus 1 minus x to the t divided by 1 minus negative x dx. And since we are in the radius of convergence, we can write this as an infinite geometric series going from k equals 0 to infinity of negative x entire thing to the kth power, and then the numerator is as it is, x to the t plus 1 minus x to the t dx. So now what I'm going to do is interchange the sum and the integral, assuming uniform and absolute convergence, obviously. So we have sum from k equals 0 to infinity minus 1 to the k that we can take out, integral from 0 to 1. Now x to the k can be distributed in the entire thing over here. So we have x to the t plus k plus 1 minus x to the t plus k dx. And integrating this is actually very trivial. This is just the power rule of integration. So this will actually become x to the t plus k plus 2 divided by t plus k plus 2 minus x to the t plus k plus 1 over t plus k plus 1. But since it's a definite integral, we need to evaluate that from 0 to 1. So at x equals 1, we'll just have a 1 in the numerator, and at 0 everything will become 0 because that will be 0 minus 0. So just looking at this upper bound, we have 1 to the t plus k plus 2 is still 1 over t plus k plus 2 minus 1 to the t plus k plus 1 is still 1 over t plus k plus 1. Okay, so that is actually our I prime of t. Okay, so now, like with our Leibniz rule every time, we need to reintegrate rather, with respect to t. And what are our upper and lower bounds? So at one bound, I of t should, equal I. So when is that possible? So notice that when uh, I of t, when t equals say 0, you have x to the 0, which is 1. So that's like saying that there is no exponential anymore. We'll just equal our original I. And in the limit as t goes to negative infinity of I of t, x to the negative infinity effectively will decay to 0, like e to the negative x in the limit as x tends to infinity. So we need to integrate from negative infinity to 0, right? From lower bound to upper bound. So integral from negative infinity to 0 of I prime of t dt by the fundamental theorem of calculus will actually give us I of t evaluated at 0, which is just I, minus I of t evaluated at negative infinity will be just 0. So I minus 0 or just I. And we know I prime of t actually, um, that is the sum from k equals 0 to infinity of minus 1 to the k, but we still need to integrate with respect to t. So what I did was I took the sum outside, again assuming uniform and absolute convergence, and had this integral go from negative infinity to 0, because only the t dependent terms are inside, right? This sum effectively, like the other part, the only k part is independent of t. So if 1 over t plus k plus 2 minus 1 over t plus k plus 1 and a dt, okay, and this is I. So I is, well, just write the sum as it is from 0 to infinity of minus 1 to the k. Antiderivative of the first term will just be a natural log of absolute value of t plus k plus 2 minus the second term antiderivative is natural log of t plus k plus 1 evaluated from negative infinity to 0. Okay, so we have sum from k equals 0 to infinity of minus 1 to the k. We have natural log using log properties, t plus k plus 2 divided by t plus k plus 1, again evaluated from negative infinity to 0. So at t equals 0, we just have a natural log of k plus 2. K is positive, so no need for absolute value. So k plus 2 over k plus 1 minus limit as t goes to negative infinity of natural log of absolute value of t plus k plus 2 divided by t plus k plus 1. So that's our expression. So notice at in the limit that t goes to negative infinity, this is a rational function, and a rational function having the same limit variable with the same coefficient and the same degree will just go down to 1, because you can see by even dividing by t, you'll have 1 plus k over t plus 2 over t divided by 1 plus k over t plus 1 over t. And in the limit as t goes to negative infinity, all the 1 over t terms will just go to 0, giving us natural log of 1 over 1. So natural log of 1 effectively, which is equal to 0. So the infinity divergent risk part is gone. So we just have sum from k equals 0 to infinity of minus 1 to the k, natural log of k plus 2 over k plus 1. Now let's write some terms. This is I. Let's write some terms now. So at when k equals 0, we just have natural log of 2 over 1, then minus natural log of 3 over 2, plus natural log of 4 over 3, and so on till infinity. So I'm going to write the negative natural logs as positive natural logs, and I'm going to flip the argument. And using again properties of natural logs, we can write them as a product. So our product basically is 2 over 1 times 2 over 3 times 4 over 3, and that goes on till infinity. That is actually our product. And this product, it turns out, of 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5, going on till infinity. I hope you see the pattern here. If you don't, we still have the next page where we prove this. This product is actually called the Wallis product. And it's an infinite product, as you can see. And don't worry, this I actually has a specific value. This integral actually has a specific value. And we can get that by actually solving the Wallis product, evaluating it. And I'm going to prove, I'm going to actually calculate the value of the Wallis product in 4 different ways. So don't worry, let's develop an intuition about this, and actually find also a general form of this Wallis product. So for those purposes, see you on the next page. Okay, so previously we had the product, the Wallis product. We defined that to be 2 over 1 times 2 over 3 times 4 over 3 times 6 over 5 times 4 over 5. I'm sorry, pattern can be slightly confusing, times 6 over 5, and that goes on till infinity. So now to find actually a general structure, a general form for this Wallis product, is not to look at each individual term as we do with most series when we're trying to generalize them, but to look at two terms together. So looking at two terms, notice that the numerator will always be even. So if we are defining a product, we will go from n equals 1 to infinity, because it's an infinite product, duh. And we're starting with 2. So, and if we let n equal 1, we need 2n, and that will ensure that all the numerators will always be even, divided by 2n minus 1, right? Because 2 times 1 is 2 minus 1 is 1. So we have 2 over 1, multiplied with, again, 2n because of the 2, divided by 2n plus 1 because we have a 3. And if you repeat that, so this is the first group. For the second group, if you take n equals 2, you'll have 2 times 2, which is 4, divided by 2 times 2 minus 1, which is 3. So we got this first term, multiplied with 4, divided by 2 times 2 plus 1, which is 5. So we got the second term. So we're having, we can represent this entire thing in terms of two group terms. And now if it pleases you, let's find the product. So 4n squared divided by 2n minus 1 times 2n plus 1. We can use the difference of squares formula to get 4n squared minus 1, and that is exactly our Wallis product. Okay, after we've actually found out a general form for our product, let's actually go on to evaluate it. Okay, so the first proof we have, number one, is, the idea for using such a thing can, come by practice, and being fluent with some formulae of some functions. Or if you want to think about it that way, what is the other product, what is a product that I proved recently, before dealing with the Wallis product, which is today? Which other product did I deal with before the Wallis product? Well, if you recall my video, we had actually proved the sine product representation. So we had sine of pi z over pi z is actually equal to product from, say, n equals 1 to infinity of 1 minus z squared over n squared. And at this point you may say, how is that helpful? But now plug in z equals half. So you have sine of pi over 2 divided by pi over 2 being equal to the product from n equals 1 to infinity of 1 minus half squared, which is 1 over 4 times n squared. And looking at the right hand side, we can also take a common denominator. So we have 4n squared minus 1 divided by 4n squared. And you may say, hey, wait, that is just the reciprocal of the Wallis product, right? Isn't it? Just because the denominator and the numerator are actually interchanged. So the reciprocal of the Wallis product, 1 over w, is sine of pi over 2 is 1. And we have a pi over 2. Taking the 2 on top, we have 2 over pi. So this means the Wallis product, taking the alternando if you want, or cross multiplication, is pi over 2. So hey, look at that. This Wallis product actually turned out to be pi over 2 using nothing but the sine product representation. Isn't that fabulous? Isn't that something amazing? But if you're thinking the video is over, well, you're wrong, because we have three other ways of proving that the Wallis product is equal to pi over 2. Okay, so on this page we're going to use gamma functions and basically double factorials to prove the Wallis product. So the Wallis product, we know, is sum from, say, I don't know, n equals 1 to infinity of well, 2n over 2n minus 1 times 2n over 2n plus 1. Let's just keep it that way. Okay, so now I urge you really to look at this 2n plus 1 over here. So in the basically just considering 2n plus 1 in this infinite product, say product from n equals 1 to infinity of, say, 2n plus 1. Forget that it was part of the denominator of this Wallis product. 2n plus 1 is actually 3 times 5 times 7 times 9, going on till infinity. So if you want to look at it that way, this is almost 2n plus 1 double factorial, because we are skipping two places when we are having this multiplication go on. So what I'm going to do, as I'm going to basically divide everything by 2, and there are actually n number of terms. N number of terms. You can check that. There are n number of terms. To be precise, let's actually represent this as a limit as k goes to infinity. So we can have k on top, just for better mathematical proving. So the last term will not exactly be infinity, it will be 2k plus 1 in the limit that k goes to infinity. Subtle difference there. So this is 2k plus 1 double factorial in the limit that k goes to infinity. So effectively there are k number of terms, right? Because the upper bound is k, so k number of terms. So I'm going to do is, so I'm going to multiply and divide by 2k times. So we have 2 to the k, and then for the k terms we can multiply 2 this way: 3 over 2 times 5 over 2 times 7 over 2 times 9 over 2, going on till say 2k plus 1 over 2, the last term, in the limit again as k goes to infinity. So k terms and 2 to the k in the denominator, 2 to the k in the numerator. It's basically multiplying by 1. So when I do that, we'll have limit as k goes to infinity of 2 to the k, and let's write it in a different order. We have k plus half dot 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 9 by 2 times 7 by 2 times 5 by 2 times 3 by 2. So notice here we have 2 to the k, and then k plus half factorial actually. So k plus half factorial, because going forward we're just reducing 1. So 1 minus 9 over 2 is 7 over 2. 1 minus 5 over 2 is 3 over 2. Sorry, 5 over 2 minus 1 is 3 over 2. 7 over 2 minus 1 is 5 over 2. 9 over 2 minus 1 is 7 over 2. So we are just reducing by 1 like a regular factorial, and the starting term is k plus half. So it's k plus half factorial, but we want to represent it as a gamma function. So k plus half plus 1, so k plus 3 over 2. But we aren't going past 3 over 2. So we aren't going past half factorial, or we aren't going past a gamma of 3 over 2. So we divide by gamma of 3 over 2, because we really don't want the terms that are afterwards, like say half and negative 3 half, and so that's like a limiting factor that we divided by. Okay, fair enough. We finally have limit as k goes to infinity of 2 to the k, gamma of k plus half divided by gamma of 3 over 2. Okay, and although this is like a diverging expression, but let's just keep it as it is. So that's the 2n plus 1 part. Now similarly look at the 2n minus 1 part. So we have product from uh, n equals 1 to k in the limit as k goes to infinity of 2n minus 1. Writing down some terms is 1 times 3 times 5 times 7 times 9, and the last term effectively is 2k minus 1 in the limit again as k goes to infinity. So in the limit as k goes to infinity, we can divide and multiply by 2 to the k, because there are k terms. 1 over 2 times 3 over 2 times 5 over 2, 7 over 2, and the last term is k minus half. So similar to what we did above before this, we can write this in terms of gamma. So gamma of k minus half plus 1, or gamma of k plus half, divided by gamma of half, because we don't want the factorial to go beyond half. Okay, and that's although this is like diverging to infinity in the limit, let's just keep it as it is. Okay, now it's time to look at the 2n. So in the product that n goes from 1 to k, or in the limit as k goes to infinity of 2n, this is basically 2 times 4 times 6 times 8 going on to 2k in the limit as k goes to infinity. And now we can basically factorize 2 from all the terms. So when there are k terms, so 2 to the k factorized out, we have 1 times 2 times 3 times 4 till k, again in the limit as k goes to infinity. So we have limit as k goes to infinity of 2 to the k, but k factorial, which is gamma of k plus 1. Okay, again diverging terms, but don't worry, let's plug everything in this Wallis product. The Wallis product is basically, now just drop the product, because we took the product individually of all these terms. So 2n turned out to be, let's have a common limit as k goes to infinity, 2 to the k times gamma of k plus 1 for 1 2n, and then for another 2n we have 2 to the k times gamma of k plus 1 again. Okay, and divided by 2n minus 1, which we calculated to be 2 to the k times gamma of k plus half divided by gamma of half times another 2n plus 1, which actually became 2 to the k times gamma of k plus 3 by 2 divided by gamma of 3 by 2. Okay, so notice the 2 to the k's will cancel out each time. So in the limit that k goes to infinity, we have gamma squared of k plus 1 over gamma of k plus half times gamma of k plus 3 by 2, and this gamma of half and gamma of 3 halves will go on top like that. So effectively gamma squared of k plus 1 is basically gamma of k plus 1 times gamma of k plus 1, and in the limit that k goes to infinity, we have basically infinity factorial times infinity factorial divided by infinity factorial times infinity factorial, because although k goes to infinity, you add half or 3 half to infinity, it will still be a really large number, or infinity. So what I'm trying to say is, you have k in the limit as k goes to infinity, that is still equal to limit as k goes to infinity of k plus half, which is equal to in the limit as k goes to infinity k plus 3 by 2, which is also equal to in the limit at that k goes to infinity k plus 1. So because of all these equivalences in the limit that k goes to infinity, this ratio will just cancel out to 1. So finally all we are left with, and mind you this is the Wallis product, all the k terms go off, so forget the limit. We have k gamma of half times gamma of 3 halves. Now the gamma of half is actually square root of pi, and the gamma of 3 halves is 1 half times gamma of 1 half by the recurrence relation. So square root of pi over 2 times square root of pi, which turns out to be pi over 2, and that is again indeed the Wallis product. And tada! We proved it again using gamma functions and double factorials. Okay, now in the third method of proving what the Wallis product actually is, let me first just write the general expression for the Wallis product. It's like really helpful for us right now. So 4n squared divided by 4n squared minus 1, or if you want to put it the other way, n equals 1 to infinity 2n over 2n minus 1 times 2n over 2n plus 1. If you actually look at Wikipedia and stuff, they write the Wallis product in terms of its reciprocal. So effectively you obtain 2 over pi, but I just like the pi to be in the numerator. I like the pi to dominate the fraction, so I keep it on top. So anyways, now this method involves proof by integration. So now to start with, consider I sub 2n to be integral from 0 to pi over 2 of cosine of 2n of x dx. And we actually tackled a similar problem when we were actually doing a MIT integration B. So please check out those two videos. They're really interesting and insightful. So what I'm going to do is bring a cosine out from the cosine of 2n. So we have cosine of 2n minus 1 multiplied with cosine of x dx. Now I'm going to use integration by parts. I'm going to integrate this while I differentiate this. So you integrate both times. So when you integrate this, you have sine x times, well, the second term is as it is, evaluated from 0 to pi over 2, minus integral from 0 to pi over 2. Now you differentiate. So you get a 2n minus 1 and cosine of 2n minus 2 of x, and this will be sine of x because of the integration process dx. And okay, so when you plug in pi over 2, cosine of pi over 2 is 0, so it will make the entire term go to 0. And when you plug in 0, sine of 0 is 0, so it will make the entire term go to 0. So this is always going to be equal to 0. And wait, I forgot to take another sign because of the chain rule. So we don't end at dx, we have a negative sine x, because when you differentiate cosine raised to 2n minus 1, we first perform the power rule. So 2n minus 1 cosine of 2n minus 2x divided multiplied by the derivative of the cosine by the chain rule, so negative sine x, and then you have a dx. So this negative, that negative will make a positive, and we'll have a sine squared. So take the 2n minus 1 outside, integral from 0 to pi over 2 of cosine of 2n minus 2 of x, and this sine squared that we have can be expressed as 1 minus cosine squared of x dx. Okay, so 2n minus 1. Now expand this bracket, integral from 0 to pi over 2 of with cosine of 2n minus 2 of x dx minus 2n minus 1 integral from 0 to pi over 2 of cosine to the 2n of x dx, just using the power rule again, and that's I sub 2n. So we have take 2n minus 1 common. This can be represented as I sub 2n minus 2 minus I sub 2n. That's I sub 2n over there. So we can take the I sub 2n's term on one side. So we have I sub 2n will equal basic algebra, and you'll get 2n minus 1 over 2n times I sub 2n minus 2, and we can recursively keep doing this, because I sub 2n minus 2 is nothing but I sub 2n minus 3 2n minus 3 divided by 2n minus 2. So if we plug that in, I sub 2n will be 2n minus 1 over 2n times 2n minus 3 over 2n minus 2, going on until n times, and that's when you'll have I sub 2n minus 2n. because we are decreasing by factors of 2 every time. So n times we'll have 2n minus 2n. So I sub 0, okay, and just write this as it is for now. So let's just write the first term 2n minus 1 over 2n, going on till I sub 0. Now I sub 0 is basically cosine to the 0 power. Cosine to the 0 power is 1. So integrating from 0 to pi over 2, just dx will give us pi over 2. So I sub 0 is pi over 2. This is I sub 2n. Now, mind you, uh, if we look at I sub 2n plus 1, so if we express this to I sub 2n plus 1, instead of 2n you substitute 2n plus 1, you get 2n divided by 2n plus 1. But since 2n plus 1 will always be odd and 2n is even, so 2n plus 1 will naturally always be odd. So if you execute this idea of subtracting 2n times, so you'll have 2n plus 1 minus 2n. So you'll just end up with I sub 1. Now I sub 1 is just integral from 0 to pi over 2 of cosine of x to the first power, or just cosine of x dx, which turns out to be sine of x evaluated from 0 to pi over 2, and sine of pi over 2 is 1, sine of 0 is 0, so we just have 1 for I sub 1. Okay, so our expression becomes 2n over 2n plus 1, and then 1 in the end. That's I sub 2n plus 1. Now what I'm going to do is I'm going to divide I sub 2n plus 1 by I sub 2n. So that's like saying 2n over 2n plus 1 times 2n over 2n minus 1, going on till say, well, let's see, in the numerator we have I sub 2n plus 1, so 1, and in the denominator pi over 2 because of I naught. And now what is I sub 2 I sub 2 plus 1? That's integral from 0 to pi over 2 of cosine to the 2n plus 1 of x dx divided by integral from 0 to pi over 2 of cosine of 2n of x dx. Fair enough. Now I'm going to take the limit as this n goes to infinity on both sides naturally. So in the limit that n goes to infinity, this is actually looking like our Wallis product general formula already, right? So let our sum run from, say, k equals 1 to n of 2k times 2k over 2k minus 1 times 2k plus 1 times we have 2 over pi. Now in the limit that n goes to infinity, you can use other methods to see that this the ratio of these diverging integrals will always be 1. So this means that this is equal to 1. This on the right hand side is equal to 1. So take the 2 over pi on that side. We have now product from k equals 1 to infinity. We applying the limit. We have 4k squared over 4k squared minus 1, multiplying the brackets. Taking the 2 over pi on that side, we have pi over 2, and that indeed is our Wallis product. So this is like another neat method of proving the Wallis product. Okay, so moving on for our final proof, which is sort of weird, this proof. But anyways, Okay, so I've simply written this Wallis product down just for our convenience. Now, this method is actually quite weird, and I can't provide like a good intuition why we start here, but it's probably because of the structure of stuff in this. So I hope you remember the Dirichlet Eta function of, say, some argument s is equal to sum from k equals 1 to infinity of -1 to the k plus 1 over k to the s. That's the Dirichlet Eta function. But there's a particular formula where we relate that to the Riemann zeta function. So the Riemann zeta function is actually the non-alternating part of the Dirichlet Eta. So that's just 1 over k to the s. So it turns out the Dirichlet Eta of s, and you can actually prove this by factorizing a 2 from each of the terms, is 1 minus 2 to the 1 minus s times the Riemann zeta of s. Okay, now I would like to actually differentiate with respect to the argument s. So we get, by the product rule, Riemann zeta prime of s times 1 minus 2 to the 1 minus s plus Riemann zeta of s times natural log of 2 because of the exponential times 2 to the 1 minus s. You can check this on a piece of paper. Pause the video if you want, if you want to do it yourself. Now plug in 0 for s. We have a Riemann zeta prime of 0 multiplied with 1 minus 2 to the 1 minus 0 is 1, so just 1 minus 2 plus Riemann zeta of 0 multiplied with natural log of 2, and then 2 to the 1 minus 0 is just 2. Now this becomes negative Riemann zeta prime of 0 plus 2 times natural log of 2 times Riemann zeta of 0. Okay, so now the Riemann zeta prime, if you take the Riemann zeta function of s like we were defined up above, and you differentiate that with respect to s, you will just have a natural log expression in the numerator. Natural log of k over k to the s. And when you plug in 0 for s, you just have sum from k equals 1 to infinity of, well, k to the 0 is 1, so we just have natural log of k. And summing natural logs like this enables us to take a product. So natural log of 1 times 2 times 3 times 4 till infinity. And although this is divergent, but in terms of analytic continuation and zeta regularization, we can actually assign a value to this. Just like the way that the sum of all positive integers is a negative 1 over 12. The same way, because for analytic continuation, we can actually take Bernoulli numbers to approximate or find an alternate values for the Riemann zeta function. So using or extending that same argument, this seemingly infinity factorial is just 1 over square root of 2 pi. So again, we can take a negative natural log of square root of 2 pi. That's Riemann zeta prime of 0. Okay, fair enough. And what's Riemann zeta of 0? Riemann zeta of 0 Okay, so for Riemann zeta of 0, it's actually not that simple as it seems. So we need to consult this equation again. And the Dirichlet Eta, actually, we can write it in terms of the infinite sum representation. So if you plug in 0 in place of s, you have k to the 0, which is just 1. So we have sum from k equals 1 to infinity of minus 1 to the k plus 1. Just simply that is equal to 1 minus 2 is negative Riemann zeta of 0. Okay, now this, if you write in some terms, is 1 minus 1 plus 1 minus 1 plus 1 going on till infinity, and this is what we call Grandi's series. This is actually a really divergent, like a special series. It's because if you rearrange the terms, so if you like club, take the one separately and then club all the remaining terms, you'll just get one. But if you club them in a different way, so if you include one, you'll get zero. Because if you say include one, make groupings like these, you eventually the terms will cancel out to zero. So it's actually, one of the cases of Riemann rearrangement theorem. But in any case, as we can assume this to be a geometric series with common ratio -1. And although in conventional sense a geometric series converges only when the absolute value of the common ratio is less than 1, less than the radius of convergence. In this case is actually equal to 1, but still we can extend that argument just for the sake of regularization and continuation, analytic continuation. We end up with 1 over 1 minus minus 1, which is half. So this means half is equal to negative Riemann zeta of 0, implying that Riemann zeta of 0 is negative half. And we can actually plug this in now into this expression that we were struggling with over here. So this means Dirichlet Eta prime of 0 is actually negative gamma prime of 0. Gamma prime is negative natural log of square root 2 pi. Negatives cancel out. We just have natural log of square root of 2 pi and negative 2 over 2. So that goes away. Natural log of 2. Yeah, that's it. Just a negative natural log of 2. Okay, so we found out one expression for Dirichlet eta prime of 0, this. Now let's look at the sum definition, the summation definition. Okay, so when we differentiate the Dirichlet eta, we have a negative alongside it. And to write some terms of this, Dirichlet eta prime of 0 is actually natural log of 2 over 1 times 4 over 3 times 6 over 5, going on till infinity. And this is actually the square root of the Wallis product, because now the Wallis product basically had terms like 2 times 2 over 1, then 4 over 3, 4 over 5. So the thing is, the even terms were being repeated and so were the odd terms, right? We can even repeat the 1. So effectively we need two of these things. So this thing inside the natural log, we need two of these. So we need this to repeat on itself. So we need to take the square of that. But taking the square of a term directly is not possible. So let's take the square of the square root, or rather the square root of the square. So that's like saying multiply and divide by 2. So we divide by 2 over here, we have a half. Natural log of the other two we multiplied goes inside and squares this entire thing. So 2, this will actually give us the Wallis product, 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 till infinity. And this is precisely natural log of the Wallis product that we were concerned about. And we already have an expression for Dirichlet eta prime of 0, that is natural log of square root of 2 pi minus natural log of 2. So take the 2 on that side and square the argument. So we've 2 times natural log of square root 2 pi over 2. So that will be natural log of of pi, natural log of the Wallis product W is equal to square is natural log of 2 pi over 4. Now take antilog on both sides. W or the Wallis product is equal to pi over 2, and that is actually another way of proving the Wallis product. Presto. Okay, so that's it for this video, guys. But before signing off, I would please recommend you guys to like, share, and subscribe to my channel. Recommend me to your friends, and please, I need more subscribers. I'm putting in a lot of work for these hard proofs and videos that I'm making. If you want my content to step up a little, you need to subscribe, guys. And in the meantime, stay home, stay safe, keep doing math, and peace out.